Hi everyone, in this video series we're going to be going through this what seems to be fairly amazing book called The Practical Electronics for Inventors, and this is the 4th edition one. Apparently this is the book that my lecturer recommends that I should go through in order for me to get up to scratch with what I need to know and what I'm struggling with in terms of currently me not being able to understand my lectures at all. So yeah, one thing I've just noticed, it's a bit funny that IC looks like it's about to be put down onto nothing. Like there's nowhere there that could go. Yeah, anyways, maybe it's Photoshop, I don't know. That looks a bit funny actually. Anyways, moving on. Okay, so what I'm going to do is I'm going to work my way through this book, and the plan is currently right now I'm studying AC voltage and current, so I need to kind of get up to there, and then I need to obviously study that as well. But I need to know the things that lead up to it. So if we look at the table of contents, what I like about this book is it gets to AC fairly quickly. Some of the other books, they might have like 400 pages on resistance and stuff like that. That might be a bit of an over exaggeration, but you'll see what I mean. So in terms of the contents page of this book, you've got theory of electronics, electric current, voltage, which is standard, right? And you got resistance, conductivity, okay, insulators, conductors, semiconductors, heat and power, wire gauges, grounds. So that's all of the basic stuff that you're going to cover as soon as you get into electronics, right? Then you got electric circuits, Ohm's law, obviously you're going to go straight into that. Voltage, current sources. I've done all of this, measuring voltage, combining batteries, open circuits, short circuits, Kirchhoff's laws, superposition, Thevenin's, Norton's, and then straight to AC. So that's literally my course basically. So everything up until here, bar a few things. For example, like we didn't cover really grounds too much or thermal heat conduction. But anyways, pretty much everything up until this point I've covered now I covered in my first year of electrical engineering. So now starting second year of electrical engineering and starting AC circuits, it seems like this book is what possibly that my university are following, and it would make sense that, you know, my lecturers recommending this. So what the plan is for me with this book is to basically start from page 1, which is not generally recommended. I mean, I could just start from AC, but I'm going to just go through and I'm going to blitz past all the stuff that I've already done. If you're a first year, you might want to take your time and go through that, but if you're a second year, this will probably benefit you because just like me, you would have done all of this stuff. I hope anyways. If you haven't done this stuff in first year, bloody hell, mate, what you been doing? Yeah, so let's get started. We're going to just scroll through. I'm going to make our way through the book, and the plan is to basically get to AC circuits, which is on page 80. So I'm hoping in this video we'll get to page 80 by the end of this video. That would be nice. So there's a lot of pages. So literally less than 10% of the book it gets to AC. Look, it's like 1,000 pages. Mad. Alright, so we've got a preface. We never read the preface. Why would you do that? We don't read the acknowledgements. No offense to the author's mother or family or whoever they're acknowledging. Introduction to electronics. Nice. Nice little diagram. Okay. Theory of electronics. Current. So we've got individual charge. We obviously, you should know that all of this stuff. Thomason, Franklin. So talking about, this is about conventional current, right? Why we do it the wrong way around, basically. Okay, again, electron flow versus conventional current flow. We're alright with that. Usually you'll find that books that have to do with practical stuff will cover that stuff. Because obviously, practically you need to understand that. Okay, so we've got power laws, which we're alright with. Got voltage, right? So we're still all okay with this, right? We're okay with combining voltage. Yep. Microscopic view of conduction for those who are interested. At a microscopic level, a copper conductor resembles a lattice of copper balls packed together in what's called a face-centered cubic lattice structure, as shown in figure 2.15. Where's 2.15? Here. And then it's like got a letter. There's no letter, huh? Okay. So where is this? Which? Okay, lattice structure. This, right? Okay. I didn't understand any of that. For copper, as well as other metals, the bonding mechanism that holds everything together is referred to as metallic bonding, where outermost valence electrons from the metal atoms form a cloud of free electrons. Okay, so this has to do with conductance. I'm okay with all of that. Okay. Resistance, resistivity, and conductivity. Okay, yeah. This book seems to be super detailed. He's even talking about the resistivity of different metals, which I suppose so. The pure water, 2.5. Air. What's air? Where is it? It didn't give it. Ooh, I shouldn't have said that word. I need to cut that bit out. So this word you cannot say on a YouTube video anymore. Sucks to be the beverage company that has that same name, right? So, human skin. Alright, so this just has to do with resistivity of different objects, materials, heat and power. We just got, what page am I on right now? Page 60 already. Oh no, I'm on page really 31 actually. Difference versus PDF page versus book page, right? General power law, right? Which tells us that if we can measure the current entering the device, P equals VI, yep. IV. This seems like I'm going to be able to skip through straight to AC, which is nice. Thermal heat conduction and thermal resistance. How is the energy transferred in heating? Within a gas, heat transfer represents transfer of energy between colliding gas molecules. Gas molecules at a hotter temperature move around more quickly. They have high kinetic energy. Okay, I haven't actually done any of this. Probably the larger question is more, should I? And I don't personally feel like I should. So let's not. I say one thing. I said, oh, I'll do the stuff that I haven't gone through, and then I see it. I'm like, no, let's not do that. The wire gauges, I know I'm right with that. The smaller the wire, the less current, obviously. Same with, think of the water analogy. Grounds. Alright, I don't really understand digital grounds. I suppose a digital ground is just a reference, isn't it then? Right? So the correct definition of an earth ground is usually a connection terminated at a rod driven into the earth to a depth of 8 feet or more. That's like a proper earth ground. So alright. I'm gonna go through this mostly I'm gonna just summarize it mostly just because I actually would like to know the difference, but I suppose for my course for my second year I don't really need to know. So yeah, catch 22 here, but I'll try and do it quickly. Let's just do types of grounds. Got an earth ground is a rod driven into the earth. How much is 8 feet? If you think about this whole social standing far apart thing that we're doing all now, they say 6 feet, right? Which is 2 meters. So 8 feet. What did they say? 8 feet? 8 feet, yeah. So it's like two and a bit meters. let's say 2.5 meters. That's a lot. Think about this. Earth to the rod. Earth. Earth. Ground. So obviously, our computers aren't earth ground, right? Okay. So the correct definition of earth ground atrium. Well, this earth ground rod is wired directly to a mains breaker box ground bar and sent to various AC outlets in one's home via a green coated or bare. I didn't know that. So it's actually all of our homes are actually earth grounded. Hmm. Interesting. Okay. So electronic equipment sharing common ground. Yep. Hot neutral ground. That's fine. Common grounding error. As previously mentioned, the ground symbol in many cases has been used as a generic symbol in circuit diagrams to represent the current return path, even though no physical earth ground is used. Got it. So there's a difference between the current return path and ground, obviously, right? This can be confusing for beginners when they approach a three-terminal DC power supply that has a positive, negative, and ground terminal. As we have learned, the ground terminal of the supply is tied to the case of the instrument. Okay. But where did they mention that? I mean, I know I kind of skipped over it a bit. Let's just put difference between earth and negative. Right? So you've got positive, got negative, and you got ground. Okay. On instruments, ground will be connected to the casing and negative is the current return path. Yeah, I'm okay with that. That's not something that I've really thought about. And you got floating return common. Different types of ground symbols. Earth ground, frame or chassis, analog, digital. The common floating return, common reference, voltage reference. You've got earth. And then you got chassis. This is like what's in a car, right? Chassis. Because obviously our cars aren't grounded into the earth. And analog digital. So floating. So analog digital floating. Okay. That's an X, and then this is a reference. Yeah, I'm quite happy with that. I mean, that's something that I have kind of wondered when I'm using multisim. What's the difference? Okay, let's skip over the rest of this now. You got basic circuit, series circuit, parallel circuit, combination of series and parallel. Hopefully you're all okay with that. Ohm's law and resistors, we're okay with that as well. Power loss and power ratings of resistors. Resistors in parallel. Current divider, we're alright with that. Resistors in parallel again. 1 over R1 plus 1 over R2 plus 1 over R3. Kirchhoff's law, voltage dividers. Nice, this is all good. This is all good stuff. Designing a voltage divider adjusted load equivalence. Okay. I feel like I should just briefly read through this, and I might make it like a bedtime task to put me to sleep or something. Reducing a complex resistor network, which we obviously know how to do. Just product over some bunch of times. Add some series resistors together. Multiple voltage dividers. This isn't something that I've really looked at. Okay. So I think from here on out, then it's basically, we're just going to get to AC now because we're already on page 64. We're going to touch on Thevenins, Nortons, etc. Combining batteries, which we're okay with. Open and short circuits, we're okay with. Nice. Okay, so we're pretty much good to go on to. Well, they put like a Wheatstone bridge of resistors here. Did they mention it? No. Just basically just for practice combining. That's okay. Even using multi-sim here. Virtual current law in action. This is a nice diagram. Very nice diagram. Look at that. It's got voltage and current there together. That's good. Thevenins and Nortons. This is a good book, you know. This is actually a very good book. I'm impressed. I don't know why I didn't use it in my first year. Real circuit. Obviously, I don't know. I'm just looking at the pictures because obviously I know this stuff, so I'm comfortable with this. I'm looking at the pictures and I'm going, these are good diagrams. These are good circuits. As I'm looking at them, I'm like, yeah, it would be good to practice on these. So, I don't know about the wording though. The wording might be complex, which we're about to find out now. So now we've gotten to AC, so let's get onto that. So I only really took notes of grounding throughout those first 80 pages, but that's fine. If there's anything that I really don't understand, you know, the author will usually mention and say, we've explained this previously in the book, you know, refer back to chapter blah blah blah, as we mentioned previously. If I get stuck on any of that kind of stuff, I'll go back and try and find it. But for now, let's get cracking with the AC circuit. I'm going to start from the beginning. Basically, I really don't know anything about AC. I've been trying to learn the bits and bobs from Google here and there, but it's been confusing. So this should hopefully give me some cement. So pop my glasses on and get some reading going. A circuit is a complete conductive path through which electrons flow from source to load and back to source. Source to load, back to source. Yep. As we've seen, if the source is DC, electrons will flow in only one direction, resulting in a direct current. Another type of source that is frequently used in electronics is an alternating source that causes current to periodically change direction, resulting in an alternating current. In an AC circuit, not only does the current change directions periodically, the voltage also periodically reverses. This is something I've been really struggling to understand, that the voltage periodically reverses. Okay, so in AC circuits, both current and voltage periodically reverse. Okay, so figure 2.77. What one? Okay, all of this. Shows a DC circuit and an AC circuit. Okay. The AC circuit is powered by a sinusoidal source, alright, which generates a repetitive sine wave that may vary in frequency from a few cycles per second to like 50 to billions of cycles per second, depending on the. Okay. So the T tells you that the current is dependent on time. Where's the T? Oh, here. It's talking about this T. The arrow's direction sets the reference direction used in the graph. The arrow direction, or this one, this arrow here, sets the reference direction used in the graph. Okay, I don't really get that. This is an ammeter, right? Got a load and you got a voltmeter. So measuring current here and we're measuring voltage here through this resistor. Okay, the positive and negative swings in voltage or current relative to a zero voltage or amp reference line simply imply that the electromotive force, interesting, okay, simply imply that the electromotive force of the source has switched direction, causing the polarity of the voltage source to flip and forcing current to change direction. Okay. The actual voltage across the source terminals at a given instant in time is the voltage measured. Hang on. The actual voltage across the source terminals at a given instant in time is the voltage measured from the 0 volts reference line to the point on the sinusoidal waveform at a specified time. So does that mean that this, if I have a voltage like this, let's say this is 9 volts, so I've got a 9 volt battery, or obviously not a battery, but a 9 volts AC, then does this count as 9 volts, right? Or more quickly, it counts as minus 9 volts, right? Because it's minus 9 volts in reference to ground, which is 0. I think that seems, I don't know. Let's just write down what they've got here because I quite like this explanation. So the positive and negative swings in voltage and current relative to a 0 voltage or amperage reference line. So the positive or negative, can you get negative current? Oh, of course you can. Yeah, that's a dumb question. Negative current or voltage. The positive or negative current or voltage is relative to a 0 voltage or amperage reference line. Is relative to a 0 amp or voltage reference line. Okay. Now I could take these notes directly onto my Notion, which is here, and I could save all of these notes into here and stuff like that. But what I prefer to do is when I'm first learning something, like actually learning and not just scoping the subject, I prefer to write physically with a pen. I know I'm using an iPad. The pencil is similar to an iPad for me. It means that I can draw these kind of images and I can get some sense to what I'm doing. And for some reason, I just interact more with the writing than I do, especially once I start copying and pasting. So I just prefer to write. I find that my retention is way higher. Okay, so the actual voltage across the source terminals at a given instant in time is the voltage measured from 0 reference to the point. So the actual voltage, yeah, is 9 volts basically. If you're going here, the actual voltage is still 9 volts. It's just negative in reference to. It'd still kill you, for example, but it would still kill you, and it's not gonna take 9 volts from you. It'd still put 120 volts into you, right? So when it comes to generating AC, the most common way to generate sinusoidal waveforms is by electromagnetic induction by means of an AC generator or alternator. For example, the simple AC generator in figure 2.78. Yeah. Okay, so it's like it's a hand crank thing. Consists of a loop of wire that is mechanically rotated about an axis while positioned between the north and south poles of a magnet. As the loop rotates in the magnetic field, The magnetic flux through it changes and charges are forced through the wire, giving rise to an effective voltage or induced voltage. According to figure 2.78, the magnetic flux through the loop is a function of the angle of the loop relative to the direction of the magnetic field. The resultant induced voltage is sinusoidal with angular frequency radians per. Why did they introduce this too quick? Now I'm just gonna see if they've mentioned this symbol prior. So we're currently on page 81. Angular. Yeah, it's not mentioned. It won't let me search for Omega. Okay, so let's just assume that this is the first instance of those, man. Let's assume this is the first instance of them mentioning that. Okay, so the resultant induced voltage is sinusoidal with an angular frequency of radians per second. I can see it's got 0 degrees, 45 degrees, 90 degrees. So I don't understand. I mean, I don't understand why these are 45 degrees and 90 degrees. If I drew a triangle there, for example, like down there, that would be 45-degree angle. So I don't really get that. But I'm going to try and just put this to memory now and just stop worrying about not understanding it. I feel like there's probably an issue in my mathematics now. It's probably affecting me more. Okay, so they're saying that this is 45 and this is 90. 5 degrees, 90. Okay, A is the area of the loop and B is equal to the magnetic field. Where are we getting A and B from? What are we referring to here? So there's the angular frequency, which is equal to D of theta. What's D? Get D from? I've got a lot of. I think I'm hit. I think I've hit a wall again. I think we're dealing with maths issue here because when they're introducing these equations as if to say, "Hey, you dumb, you should have done this. You should know this math stuff." And I don't know, like just look at look at this. This to me is like not English. You may as well write this part here. May as well just be in Mandarin. Okay. Right, I'm gonna continue, and if these equations get introduced rapid without any like dumb explanation for me, then I'm gonna have to just stop and then back on with the K-Stroud maths book. Okay, so real AC generators are of course more complex than this, but they operate under the same laws of induction nevertheless. Other ways of generating AC include using a transducer, i.e. a microphone, or even using a DC powered oscillator circuit that uses special inductive and capacitive effects to cause current to resonate back and forth between an inductor and a capacitor. Okay. Why is it important? There are several reasons why sinusoidal waveforms are important in electronics. The first obvious reason has to do with the ease of converting circular mechanical motion into induced current via an AC generator. However, another very important reason for using sinusoidal waveforms is that you differentiate or integrate a sinusoid. Is that if you differentiate or integrate a sinusoid, you get a sinusoid. Applying sinusoidal voltage to capacitors and inductors leads to sinusoidal current. Okay, I don't understand why that's a benefit, but let's just write that down. So benefits of AC. So number one, you can use was it rotational generators? What did they call it? Circular mechanical motion generators. You can use circular mechanical generators, mechanical motion. Circular mechanical motion. Is that like boiling water and having it spin a turbine, or using a wind turbine to generate electricity? I assume. They use circular mechanical motion into induced current. Huh? Oh no, converting. Use circular mechanical motion to uh, generate electricity, generate current. And number two, what was it? Something about putting a sine wave in, you get a sine wave out. That was it. If you differentiate or integrate a sine, what does it mean to differentiate or a sinusoid? Perform or mark differently from other such things to distinguish it, to change or alter, to perceive the difference in or between. That's what I understand to differentiate to mean, but that doesn't seem like the manner in which they're using it. But calculus. I haven't actually studied calculus, and I feel like I absolutely should. Differential calculus is a subfield of calculus that studies the rate at which quantities change. Differentiation allows us to find rates of change. Okay, so it seems to have something to do with rates of change. So, however, another very important reason for using sinusoidal waveforms is that you differentiate rate of change. Okay, anyways, just ignore the red. Ignore that. If you integrate a sinusoid, you get a sinusoid. All right. Okay. I don't know what it means to integrate a sinusoid. If you integrate a sinusoid, you get them out. Is that the correct terminology? Out. Okay, so number 3, it says the most important thing, benefits of AC involves the ability to increase voltage or decrease voltage at the expense of current by using a transformer. Okay, so most important. This is really the one I need to remember. So the ability to increase or decrease. So increase or decrease voltage using I don't really know what this means. Using what was it? Transformer. Okay. In DC, a transformer is useless, and increasing or decreasing the voltage is a bit tricky, usually involving some resistive power losses. Okay, well, yeah, you can decrease the voltage easily with DC, but I don't know how you'd increase it. Transformers are very efficient, on the other hand, and little power is lost in the voltage version. Okay. Uh, uh, okay, I don't need to take notes on that. Water analogy, love it. Absolutely love it. If you watch any of my other videos, you know I love a water analogy. This is everything of electricity should just be explained with water analogies. It just goes. It works so perfectly. So obviously, it's not. I get that it doesn't work perfectly. I'm just saying. So figure 2.79 is left, right, or both of them. Both of them. Shows a water analogy of an AC source. The analogy uses an oscillating piston pump. Where's the pump? Yeah, I can't see it. It's probably low down. Oh, this is the pump. Okay, so using an oscillating piston pump that moves up and down by means of a cam mechanism. Okay, so you're rotating it, and the pump's moving up and down, driven by a hand crank. What am I looking at here? Get it? So you've got a pump with some water in it. As you pump the water, obviously you're squeezing the water together, so you're getting more and more of a high pressure. Just like if you had a water balloon and then you squeeze the water balloon. Okay, water resistor, increasing pressure. Why does it say alternating? Well, because you're cranking, because you're spinning the hand crank. Okay, and so it's flipped on this side now. It's flipped, so you're hand cranking it. Oh, okay, sorry, you're spinning it this way. Okay, you're spinning it clockwise, and he's spinning it. No, you're still spinning this clockwise as well. What's the problem then? Oh, okay, I get it, because the crank is bigger on this side, smaller on that side. Got it, got it. Okay, so as nice. I got it. So the piston's going up and it's creating pressure there. And then when it's coming down, it's creating the opposite pressure down here on this side. So you're constantly creating pressure, low pressure, pressure, high pressure over here, then high pressure over here. High pressure over here, high pressure over here. Low pressure here, then you crank it. Yeah, got it. That's very clever. Okay. I wanna obviously I wanna keep this example with me, so I'm gonna take a picture of it. iPad. Let's do AC water analogy. Best picture, but crap. Oh crap. That messed up. Inside, let me check it. There you go. AC water analogy. Got it. Okay. So in the water analogy, water particles on average appear to simply swish back and forth as the crank is turned. In an AC electrical circuit, a similar effect occurs. So things are a bit more complex, of course, always. One way to envision what's going on is that within a conductor, a conductor, the drift velocity of the sea of electrons is being swished back and forth in a sinusoidal manner. Okay, the actual drift velocity and distance over which the average drift occurs are really quite small, fractions of a millimeter per second range, depending on conductor and applied voltage. In theory, this means that there is no net change in position of an average electron over one complete cycle. Yep. It is not to confuse with individual electrons' thermal velocity, which is mostly random and at a high velocity. Also, things get even more complex when you start applying high frequencies, where the skin effect enters the picture. More on this later. Thank you for not going into that now. Pulsating DC. Pulsating. Okay. Pulsating direct current. Okay. If current and voltage never change direction within a circuit, then from one perspective, we have DC current. Yeah. Yeah. Even if the level of the DC constantly changes. Ah, okay. Like as if you was using pulsive modulation or I don't know, something like that. Like if you switch on and off the battery, the current still kept going the same way, but you had a varying voltage from, or if you just had a dodgy power supply or something. So, for example, in figure 2.8, the current is always positive with respect to 0, though it varies periodically in amplitude. Whatever the shape of the variations, the current can be referred to as pulsating DC. If the current periodically reaches 0, it is referred to as intermittent DC, meaning that it's cutting out. Got it? So let's put pulsating DC, and then we got intermittent DC. Intermittent DC. Since I started watching UFC, I can't get. I now think of DC as Daniel Cormier instead of as direct current. Okay, so pulsating DC. So pulsating DC is the varying voltage. Varying voltage that doesn't reach zero, right? Always positive. Always positive. Meaning like above zero. And intermittent is varying voltage. Sometimes it's zero. Every DC pulsating. Okay, so here you can see it's pulsating, but it's not going below zero. Yep, comfortable with that. Let's just do this. So, okay, zero, and then you got something like that, right? So you got 0 volts there, say 12 volts here. You got pulsating DC, and then intermittent. We don't have a picture of intermittent, do we? No, but intermittent would be like, oops, across zero. Okay, wouldn't I don't know. I don't really know what it'd be like. Something like that, maybe. Anyways, I don't know. It's fine. We'll leave it like that, anyways. I get it. I get it. I understand it. I don't know if I can draw it though. So from another perspective, we may look at intermittent and pulsating DC as combination of AC and DC current. Yeah, I get that. Special circuits can separate the two currents into AC and DC components for separate analysis or use. There are also circuits that combine AC and DC currents and voltages. Okay, interesting. So combining sinusoidal sources. Besides combining AC and DC voltages and currents, we can also combine separate AC voltages and currents, such combinations will result in complex waveforms. This is like adding together two AC signals, getting one complex waveform. Okay. Figure 2.8 shows two AC waveforms fairly close in frequency and a resultant combination. Figure also shows two AC waveforms dissimilar in both frequency and wavelength along with the resultant combined. So two that are similar and you combine them. I get this one. This one's I understand. Oh crap. I understand this one here. I'm cool with that. That makes sense. Think about it. You got this one. You add this one to it. You get that makes sense. This one, I don't know what's happening here. You got so one. This one's obviously faster by 500 hertz. See it? When you add them together, you get a 500 hertz. Like it's like a, is it like a minus? You've subtracted them, but then you get like a squiggly. I don't get that. I don't get that, but that's fine. I get the other side. So let's put adding AC signals. So you've got similar waveforms. Take a picture of that. I'll crop. Okay, so you've got similar waveforms there being added together, and then you've got the two dissimilar ones. Dissimilar waveform. A, B, A plus. I suppose it's called V1 and V2, isn't it? V3. Let's just avoid confusion. Call it V1, V2, V1 plus. Okay. And let's add the dissimilar waveforms. This actually looks like a bearded person. See the eyes. Got the eyes there. Nose. Mouth. Anyways, alright. So got this one as well. Okay, so again you got V1, 2. I mean I could just put these in the middle actually. There you go. Okay. I'm comfortable with that. On the left, you got two AC waveforms of similar magnitude and close in frequency form and close. Similar magnitude and close in frequency. Okay. Two AC waveforms that are similar magnitude and close in frequency that form a composite wave. Note the points where the positive peaks of the two waves combine. Interesting. Okay. So the positive peaks where the two waves combine to create high composite peaks. So where the two peaks line up, you get high peak. Interesting. What happened here? They don't line up again after that? Right, yeah, they don't. Interesting. Okay, so that's something that's worth noting down, isn't it? Just like this. Like this. Like this. So note where the peaks match forms, what did it say? Forms a high peak. Okay, this is the phenomenon of beats. This phenomenon of beats. Right then, phenomenon of brackets. So I don't think I'm a weirdo when I see this again. The beat note frequency is F2 minus F1. Beat note frequency. What? Beat note frequency. Okay. Beat note frequency is equal to F2 minus F1. 500. Don't get that. Okay. So on the right, you got two AC waveforms of widely different frequencies, form a composite wave in which one wave appears to ride upon the other. Yeah. 10,000 hertz wave is riding on the 1000 hertz. Later, we will discover that by combining sinusoidal waveforms of the same frequency, even though the amplitude and phase may be different, you always get a resultant sine wave. By combining sinusoidal waveforms, so it says later we're going to discover that, so I could skip this for now, right? Later, we will discover that combining sinusoidal waveforms of the same frequency, even though their amplitude and phases may be different, you always get a resultant sine wave. This fact becomes very important in AC circuit. I didn't understand that. So we will discover that by combining sinusoidal waveforms of the same frequency, which is like how fast they go per second, right? Even though the amplitude phases again, I can't phase is like if it's lagging or he hasn't touched on phases yet, so Wolf hasn't touched on phases, so even that's why he's saying later, because I don't know what phase is here. Okay. I'm keen to try and not let the videos get too long, just because it becomes a headache for me uploading it. My computer's not good enough, or my laptop is. So I'm gonna end this one here, and then I'll have a coffee break, then crack on with AC waveforms. So catch me in the next video. Peace.